In these videos, I am going to explain the concept of rank of a matrix. For that, we need certain preliminaries about vector spaces. So I will start with a brief overview of those concepts. Now, whenever we want to visualize vectors, a good idea is always to think about R3, which is a vector space over the real field, and think of every vector in it as an arrow, like this. So this is the origin, and that's the tip of the arrow. Now if I multiply this arrow with a number, say a number which is greater than 1, in that case the arrow will stretch. And if I multiply the vector with a number which is less than 1, a positive number which is less than 1, then it will shrink. If I multiply it with a number which is negative, then it will face in this direction. So if I consider all possible multiples, all possible scalar multiples of this arrow, in that case we will get, quite obviously, the entire line through that vector. We call this the span of this vector. So it is the set of all multiples, scalar multiples of a vector. The situation is pretty much similar even if I have got two vectors instead of one. So I have shown them as two arrows coming from the common origin. Now in this case we do not just talk about scalar multiple of them separately, but we take a scalar multiple here and a scalar multiple here, and I also allow to add them, that is I take a linear combination. In this case the span is defined to be the set of all linear combinations of these two vectors, and you should already know from whatever we have already studied that the span will be the plane passing through these two vectors. So remember that we are working in R3, so don't think of this just as something flat that is drawn on your book, but something that is there in R3, it can rotate in R3. Okay, now suppose I add yet another vector to this. So here I have a third vector, and I ask the question, what is the span of these three vectors? Now that depends, the answer depends on whether this particular vector lies in the plane that is already spanned by the first two vectors. In this example, you cannot see it, just by looking at it you may not be able to understand it, but if I rotate it slightly you will see that this new vector lies again in the same plane, so it brings no fresh contribution. So the span of these three vectors is the same as the span of the first two, namely the yellow plane that I have shown. However, had this new vector been not in the plane, slightly off it, in that case that vector will bring some fresh contribution, so the span of these three will be entire R3, it will fill up everything. So contrast this situation with the situation that I showed just now, namely where this particular vector was lying on the plane. Here it was not bringing any fresh contribution, so the span did not increase even if I included that. So if I want to say that this plane is guarded by these three guards, by guarding I mean you can generate any vector in the plane as linear combination of these three, then you can actually throw away this third vector. That is not bringing any fresh contribution. But once you have thrown away that, the last two vectors, the first two vectors, none of them can be thrown away because they are not along the same line, so each of them is bringing some fresh contribution. That brings us to the concept of linear independence. We say that the first two vectors were linearly independent, and that is the smallest possible set that is required in order to generate the entire plane, in order to span the entire plane, and that number, that there were two such, we call it the dimension of the space, because there is a non-trivial theorem which says that whatever spanning set you take, if you keep on throwing away the unnecessary ones, for example in this case this particular vector was an unnecessary one, if I throw that away we are left with only two. So whatever spanning set you start with, if you keep on throwing away unnecessary things, then the smallest set that you will get in this way will always have the same size. In this case, the size will be 2, and that size is called the dimension of this plane, of this subspace of R3. So the dimension is defined as the size of the smallest possible, the size of R smallest possible generating or spanning set. So that is something that you must remember. Now here is one thing which is very important to understand. This is what we will use again and again when you discuss ranks. It is like this. Suppose you are given a set of vectors, say v1, v2, v3, 3 vectors. Then they span some subspace and it has a dimension. Now instead of taking v1, v2, v3, I take some linear combinations of v1, v2, v3. Maybe v1 plus v2, v2 minus 100, v3, like that. I take a bunch of linear combinations of v1, v2, v3. They will span some subspace. What can you say about this subspace? This subspace can at most be the subspace spanned by v1, v2, v3, because by taking linear combinations you can never go out of the subspace. So you are always inside that subspace spanned by v1, v2, v3. So by taking linear combinations, the dimension can never go up. It can stay same or it may come down. For example, if your first linear combination is v1 plus v2, the next one is twice v1 plus twice v2. The third linear combination is thrice v1 plus thrice v2. You understand, I am not doing anything other than v1 plus v2, only scalar multiples of that. So in this case, I am reducing the dimension to just 1. So taking linear combinations might reduce the dimension, might keep the dimension same, but it can never grow the dimension. This is a very important concept that you should remember. Okay, so that's all the preliminary that we needed. Now whatever we have learned, if I cast them in the language of matrix, we will get the standard theorems about ranks. So we need to know how to translate statements in terms of vectors to statements in terms of matrices. Now for that, first of all, we should cease to think about a matrix as a rectangular array of numbers and start thinking about them as a list of vectors. So whenever you are given a list of vectors like this, 1, 2, 3, 4, v1, v2, v3, v4, think of them as bunched together to produce a matrix. So they are bunched together as a matrix. So a matrix is nothing but a collection of columns. So when I say here is a list of vectors, think of a matrix. Whenever I say here is a matrix, think of a list of vectors. So that is the first step in the translation process. So whenever you have a concept about vectors, you should try to translate it in terms of matrices. That will give you a more compact representations together with some other benefits that we shall discuss pretty soon. So the first most important concept that we have seen so far is the concept of a linear combination. So whenever I give you a linear combination of certain vectors, that is, I give you a list of vectors and for each one of them I give you a scalar multiplier. Whenever you have this situation, think of these as a matrix times a vector product. So you bunch these 3 vectors as columns to produce this matrix and you collect all the coefficients as another vector. If you multiply this matrix with this vector, convince yourself that you get precisely this. Now, if you have ever wondered why matrix multiplication is defined the way it is, this is the main reason. In order to compactly express linear combinations. So that's the main motivation behind this. Now, in many cases, we start with a list of vectors, that is a matrix. Then we want to construct a list of linear combinations. Here I have shown only one linear combination. Now suppose I want to get another linear combination, which means I will be using some different scalars in place of these things. So I have shown some different scalars. which I am showing with this little tiny boxes with a little diagonal black lines, which means they are new values. Then how do I express these things again in terms of that? Of course, I can again rewrite them separately, but I won't do that. I have already stacked my vectors into one matrix. The vectors have not changed, so the matrix will not change. I will merely collect these new scalar coefficients as yet another column, and I will write it in this way. So I have the same matrix, but now I am multiplying it with another matrix, not just a vector. Each column of that matrix gives me the coefficients of some linear combination. So this gives me a list of 2 linear combinations. The first one comes with the first column coefficient, the second one comes with the coefficients given by the second column. Thus, matrix-matrix multiplication simply means a list of linear combinations. So you have already seen how we can translate various results in terms of vectors to matrices. We have already seen this. A list of vectors may be considered as a matrix. Linear combination may be considered as matrix times vector. And a list of linear combination is a matrix times matrix. The next in the line is whenever you are given a number of vectors, a list of vectors, v1, v2 up to vk, and you want to talk about its span, that is same as the column space of the matrix which is made up of v1 to vk as its columns. That is pretty straightforward. Just a notation. All these things is just a notational translation. Now if all these v1 to vk are linearly independent, that is each of them brings a fresh contribution, that means this matrix where the first column is v1, second column is v2 up to vk, this matrix is full column rank. That is the definition. Full column rank is same as linear independent. So instead of saying that this is a linearly independent set, I will say that the corresponding matrix is full column rank. Now this uses the term rank, but I have introduced this before I have talked about rank. So this is a single word. So consider this as a single phrase. It is not that full column is an adjective which is applied to rank. Full column rank is a complete concept which means that the columns of this matrix are linearly independent. Next comes the most important thing. Dimension of the span of these things, that is called the rank of the matrix. Now there are some equivalent ways of defining rank, but this is the definition which I would suggest as the most intuitive and most useful definition. We shall see the other definitions later. So whenever I give you a matrix and I say that its rank is 5, then understand that you take all the columns, so you get a number of vectors, a list of vectors, the dimension of the span is 5. So that is the definition of rank for our discussion. Now comes the first non-trivial thing. Whenever we take a basis, that is, we are given a list of vectors and we believe that all these vectors are really not important, you can express them in terms of a smaller number of vectors, then you talk about a basis. The corresponding version in terms of matrices is called rank factorization. Let's take a simple example. Suppose I give you these vectors. The first vector is 1, 2, 0. And the second vector is 2, 4, 0. Now you can say, oh, well, I'll give you one more. Suppose it is 50, 100, 0. And you quickly recognize that all these things are multiples of this 1, 2, 0. So if I consider the span of this set, that is basically same as the span of this one or this one or something else. And you can write this as this is my basis, and then this is 1 times itself, 2 times that basis, and it is 50 times that basis. I can express that as rank factorization. I will consider this as a matrix 1, 2, 0, 2, 4, 0, 50, 100, 0. Whenever I have a list of vectors, I will always consider this as a matrix. And then this is, just write down the basis, which happens to be here 1, 2, 0, followed by all these multipliers 1, 2, 50. So this is really nothing new. It is just a combination of the first and the third. List of vectors is a matrix. Then I said that look at a basis. A basis is again another list of vectors. In this case the list is singleton, so it is just a column vector. And whenever you have a list of linear combinations, that is nothing but matrix times matrix multiplication. Hence I have this matrix times this matrix. The columns here will give you the basis and the columns here will give you the coefficients. So that is a rank factorization. So in general, the rank factorization definition will be, someone gives me a, well, I will just erase the board. So someone gives me A, M cross N, and tells me that rank of A is equal to R. So I understand that this is basically made up of n vectors. Call them A1 up to AN, and all these vectors are of length M. Now if you look at the span of this set, that is R, so only R of them are linearly independent. So you pick any R, you pick any basis of the span. So suppose I take a basis which is B1 up to BR. The basis will be of length, this dimension. Then A1 can be expressed as a linear combination of B1 to BR. A2 can be expressed as a linear combination of same B1 to BR. So you create a matrix from this, you call it B. I am using just this translation scheme. I had this matrix, from this I went to a list of vectors. I extracted a basis which is a list of vectors, I go back to the matrix notation. Now each of them can be expressed as a linear combination. So I have a list of linear combination. I will go into a matrix to matrix multiplication. So this one will be M cross R. And for the first one, you will have some coefficients. So suppose your A1 happens to be whatever, say C11 times B1. Then you have got, say, C21 times B2. Blah blah blah, CR1 BR. So you can express this as a linear combination of this thing. So what is the first thing? Linear combination is matrix times vector. So here you will write C11 blah 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 CR1. You come to the next one. The same story. You write C12 CR2, and you go on doing like this until you come to the end. So you will write C1n CRN. So basically you have written it as B times C, M cross R, R cross N. That is rank factorization, which is same as taking a basis. So whenever in any vector space argument I will need to say take a basis in terms of matrix, I will say consider a rank factorization. It can be written in a much more succinct way. Since the columns of B forms a basis, so I immediately can say that this is a full column rank matrix. I can also say rank of B is equal to rank of A, which is equal to R, because I have precisely squeezed out all the redundancy from the AIs to get my B1 to BR and expressed everything in terms of that. So you have come to the end of explaining the concept of rank factorization. Always remember it as the matrix version of finding a basis. The next thing that we want to do is to find rank of some obvious matrices. rank of the 0 matrix goes without saying is 0, which you may not have observed is that if a rank of a matrix is 0, that is actually if and only if A is the 0 matrix of whatever order. So rank 0 implies that the matrix has to be 0, pretty trivial. If I take rank of identity matrix of order n, goes without saying that this will be n. And how do you show that? You just consider the columns. The columns are nothing but your Euclidean basis vectors. So they are all linearly independent and there are n of them. So the dimension has got to be n. Well, if I take a matrix A m by n, then rank of A must definitely be less than or equal to n, because I consider A as a list of n vectors, all the columns. Now each one of them may provide fresh contribution, in which case the rank will be exactly equal to n, or some of them may be just linear combination of the rest, in which case the rank will be less than n. It can never exceed n. Now the rank cannot also exceed m, the number of rows, because all these vectors are sitting inside an m-dimensional space, because each column has got m numbers in it. So if you consider your field to be say R, then all these things are entry of Rm. So the entire space has dimension m, and you are just working with the rank of the dimension of a subspace that sits inside that. So each dimension can never exceed m. As a result, the rank of a matrix must be less than or equal to the number of columns. Also, it must be less than or equal to the number of rows of the matrix. Okay, suppose I give you a matrix m cross n1, and I give you another matrix m cross n2. So it is like this and it is like this. Same number of rows but different number of columns possibly. And I append them side by side to produce a big matrix which is m cross n1 plus n2. What can you say about the rank of this fellow? Well, suppose I tell you that the rank here is R1 and rank here is R2. So there are only R columns in A that can generate the entire column space. All the others are just linear combinations of them. Similarly here for B, there are only R2 that can generate. So when you put all those things together, those R1 and R2 are still there, but the span of these things may slightly overlap the span of that thing. So we cannot say whether after you have taken this R1 into account, whether you will need all these R2 or not. As a result, it should not come as a surprise that rank of these can be at most R1 plus R2. It cannot exceed. It is just like this intuition, that inclusion-exclusion thing. If there are 4 points in this set and there are, say, 3 points in this set, then the union can have at most this plus this. It may not be exactly plus if there is any overlap. Similarly, the span of this R1 and span of this R2, if there is some overlap, that will have some redundancy here. So I can say this is less than or equal to R1 plus R2. I will write it as rank of R plus rank of B. So that is a very simple way to see this result. That's an important result. Now what happens if I take two matrices and attach them vertically, one on top of the other, instead of side by side? So here I have got two matrices that are attached one on top of the other. They must have same number of columns for this to happen. I want to know what can I say about the relationship between rank of this and the rank of the big thing. I claim that if I call this A and I call this B, then rank of this fellow must be greater than or equal to rank of A, and also greater than or equal to rank of B by similar argument. So the main idea is this: suppose I say rank of A is equal to R, which means there are certain R columns here which forms the basis of the column space of A. Everything else is a linear combination. Now when I consider the entire thing, these R things are linearly independent, so you cannot express any one of them as a linear combination of the rest. if I extend them to the entire thing in B, still they will remain linearly independent because this part already is not matching. So if you say, well, this is actually linearly dependent on the rest, so there is a linear combination of these which will give me this column. If that is the case, then of course the corresponding linear combination of the top part will give the top part of this, which is not the case. So if these things are linearly independent, extending them will continue to keep them linearly independent. There is fresh contribution already in this part. So even if there is no fresh contribution here, each one of them is bound to have some fresh contribution already from the top part. So when I extend them, I may get some further things which are linearly independent, but the part that is already linearly independent stays so. As a result, the number of linearly independent columns here must be greater than or equal to number of linearly independent columns only in the top part. As a result, I get this result. Rank of this big matrix is greater than or equal to rank of A. Similar argument will show that rank of this is greater than or equal to rank of B as well. Now just put these two arguments together and we are going to get a useful result which says the following. Suppose I have a big matrix and I take any submatrix. What can you say about the rank of this submatrix as opposed to the rank of the bigger matrix? Rank of this must be less than or equal to rank of the whole thing, which is intuitively quite natural. Smaller things should better have smaller ranks, and the proof goes like this. You just extend it like this, and you will say that this part is obtained by appending this with this. So I first consider this part. So by whatever we discussed just now, I can say that rank of this will be less than rank of the bigger thing. So I have got this, so rank of this is less than or equal to rank of this thing. Now you extend it further. I am still appending some further stuff. So this is less than or equal to rank of this. Now I am appending columns. I know whether I append rows or append columns, rank can only grow, it can never go down. Either it remains the same or it increases. So rank grows. It grows here, it grows here, it grows here, it grows here. So rank of the entire thing must be greater than or equal to rank of the small thing. Very intuitive thing, very easy to remember. Now what can you say about rank of sum of matrices? Same argument. I start with two matrices A and B. I want to know about this. Of course, before I can add, they must have been having the same size. Well, I consider them like this. You have got A, you have got B. Same size. Now I know if I put them side by side, I create this matrix, then its rank is less than or equal to rank of A plus rank of B, the way I said. Now when you add, what are you doing? You are basically adding this fellow with this fellow, right? Now when you add two vectors, you are creating a linear combination. So instead of considering all these vectors, you are considering certain linear combinations of them. This plus this, this plus this, this plus this, like that. We know that by taking linear combinations, dimension can never go up. So I can see that the dimension of A plus B, or the rank of A plus B, must be less than or equal to rank of AB. By this I mean, I will put a colon, meaning that they are just put side by side. It is not A times B. A colon B means A and B put side by side. And that we already know is less than or equal to rank of A plus rank of B. So we have a nice result, somewhat like a triangle inequality. Rank of A plus B must be less than or equal to rank of A plus rank of B. Now what can I say about product? Well, rank of AB. The moment you see product of two matrices, you know that you have to think of it as a list of linear combinations. So I have got A, I have got B. So I consider A as a list of vectors and B as a list of coefficients. So This is nothing but, the columns of AB are nothing but linear combinations of columns of A. We know that by taking linear combinations, we can never increase the dimension. So we immediately see that all the columns of B must be just linear combinations of columns of A. As a result, this must be less than or equal to rank of A. Indeed, we can make a stronger statement. It is not just the dimensions. You can say column space of A is a subspace of column space of A, which is a stronger statement. The subspace is contained inside the subspace, which necessarily forces that its dimension must be less than or equal to this dimension. So we can make this stronger statement. So rank of AB must be less than or equal to rank of A. Notice that because this multiplication is not commutative, just from this argument I cannot say the relationship between rank of AB and rank of B. There is a relationship which we are going to come in a second. So far we have been thinking of a matrix as a list of its columns. Now why not think of them as list of its rows? You can naturally guess that there is hardly anything new to be obtained that way, because it is just a matter of writing. If you just turn the paper around, the rows becomes columns. True. So you cannot expect some very fundamental result coming out of by just writing the rows as columns. However, something interesting happens if you consider the same matrix both as a collection of columns and as a collection of rows. The same matrix. Then something rather interesting happens, and that actually justifies why we prefer the matrix notation over the vector notation. So far, I have said whatever you can do in terms of vectors, you can do in terms of matrices. Whatever you can do in terms of matrices, you can do in terms of vectors. That is not entirely true. You can do something extra in terms of matrices, which is what makes matrices so very, very powerful. Let's take a look at that. In order to start the discussion, I will just introduce this notion. Suppose I have a matrix M cross N. I can think of it as a collection of N columns. Then I can look at its span, its column space, and its dimension. Dimension of column space of A. I can also consider this as a collection of M rows. The corresponding space spanned by the rows will be RA, row space. This also has its dimension. I have defined this to be the rank of the matrix. That was the definition that I used. It is interesting to say that if I do the other way around, I will get some other number in general, right? And remember, these two things are quite different, because if it is M cross N, then column space of A resides in Rm, assuming that the field is R, because all the columns are of length M. On the other hand, all the rows are of length N, so this resides in Rn. So they are quite different objects. This has a dimension, that has a dimension, and a surprising, rather counterintuitive fact is that these two dimensions happen to be the same, whatever matrix you are working with. In order to show that, I will have to use some different notation. So I will call this the row rank of A, and I will call this the column rank of A. So I will call this col A, and I will call it row A, bad notation and by no means standard. Column rank of A and row rank of A. This is what I have called rank. I am going to show that these two things are actually the same. These are not standard notations because no one really needs them except for proving this result. After you have proved this result, you really do not care about giving them different names if they are already the same. The proof that we are going to present now may be a little tricky. It's not long, it's pretty short. The steps are not difficult, but the way I am thinking may not be that obvious. I will be using nothing other than the translation scheme that I talked about. I will extract a basis and express all the columns of A as linear combinations of them. That is, I will consider a rank factorization. So I will consider a rank factorization of A, which means I will take a basis of the column space of A. I know its size will be this thing, that is the dimension. and I will express all the columns as linear combination of those things. So I will take a rank factorization, as you already know. So I will say this is m by n, then this is m by column rank of A, column rank of A cross m. These are my basis vectors, these are the coefficient things. Okay, so what can I say about this? I can say the following things. Well, let's take a look at C. What can I say about row rank of C? Row rank of C. Now, row rank of C is definitely less than or equal to number of rows of C. No one can argue against that, because row rank of C has to be less than or equal to number of rows of C, because not all the rows may have fresh contributions. So number of rows of C I can see is column rank of A. So I get this result. Now I need to somehow link it up with row rank of A. Let's see how I can do that. I claim that when you write it in this way, this is an interesting thing which I should have possibly mentioned. Just as if I write B times C, this is a linear combination of the columns of B with coefficients from C. Just look at it from the different direction. This is also linear combination of the rows of C with coefficients from the rows of B. If you are not quite convinced, think of it like this. I have a number of rows in C and I consider just a row vector, cross, cross, cross. You understand, when you do the multiplication, this multiplies this, plus this multiplies this, plus this multiplies this. So, the rows of A are nothing but linear combinations of the rows of C, which immediately tells me that row rank of A can never exceed the row rank of C, because by taking linear combinations, you can never increase dimension. So put them all together, you get row A less than or equal to this, that in its turn is less than or equal to this. So row rank of A must be less than or equal to column rank of A. And I have not made any assumption on A. This holds for any damn matrix out there. In particular, it also holds for its transpose. I will denote my transpose by the prime symbol. And it goes without saying that what I call row rank of A prime is same as column rank of A, because transposition just swaps rows and columns. And this similarly is the row of this. So I have both the inequalities which forces them to be equal. Pretty counterintuitive argument when you consider that I suddenly started magically by saying let's consider the rank factorization and look at row of C. So I did not really link up row rank of A with column rank of A. I linked it up with the intermediate quantity which is row rank of C. Pretty tricky if you are not told that this is the way to go. This is by no means the only way to prove it, but I find it quite counterintuitive, both the argument as well as the result, because these two as spaces are just as different from each other as possible. They sit inside different worlds. One sits inside Rm, the other sits inside Rn. How on earth are you going to guess that the dimensions are the same? Well, this is a wonderful fact that the dimensions are the same. Now earlier I told you that if you take a rank factorization, A equal to B times C, and it's a rank factorization, that is, it is m by n, m by r, r by n, where r is rank of A. Now we know it is both column rank and row rank. I say that the columns of B are linearly independent. Now you also know that the rows of C are also linearly independent. So the columns of B gives you a basis of the column space of A, and the rows of C gives you a basis of the row space of A. So there are two types of basis extraction involved inside this rank factorization. I told you just now that the language of matrices is more powerful than the language of vectors, and the main reason for that is what I mentioned, is that you can go from the row representation to the column representation. And that is very important, because whatever you can do in terms of matrices so far that we saw, you can think of it as a bunch of columns or maybe as a bunch of rows. But now with this result that row rank is same as column rank, that opens up an entirely new world because of the following thing. Suppose I give you some vectors, say 3, 2, 1 and 5, 4, 2. So that is something which it has a span. But now you can suddenly start thinking of these vectors 3, 5, 2, 4, 1, 2. Now geometrically it is quite difficult to connect these two vectors with these three vectors. So these are 2 arrows in R3 and these are 3 arrows in R2. So just by thinking about vectors, it is difficult to come from here to here. Yet we can see that the dimension of the space spanned by them happens to be equal to the dimension of the space spanned by them, and for this all that you have to do is basically consider this rank of A is same as rank of A transpose. That's what you prove. Row rank here is column rank here here is row rank here. Since they are equal, rank is preserved under transposition. Now matrix transposition, which may look like the most harmless operations possible, it is one of the very first operations that you have possibly learned in terms of matrices. It is something that has no obviously easy analog for vectors. Think of it as a collection of 2 arrows and think of it as a collection of 3 two-dimensional arrows. It's very difficult. Now, plenty of research has been done about making this intuitive. Instead of making this just as a trick, you just turn it around and something happens, the rank remains unaltered. Can we sort of visualize it? And that gives rise to a very rather somewhat advanced concept called dual spaces. Even after you know it, you will have to agree that dual spaces are far less easy to work with than matrix transposition. So this idea that you are working in one world, then suddenly you transpose and go into a different world, many problems that are difficult in this world will become easy in that world and vice versa. That is what gives matrices its additional power over the language of vectors. Now let me discuss a little bit about one class of results that involves full rank matrices. By full rank I mean both full column rank matrices where the columns are linearly independent, as well as full row rank matrices where the rows are linearly independent. If both these conditions hold together, then you get what is called a non-singular matrix. Now let's take them up one by one. Suppose I first consider full column rank matrices. A is full column rank, which means that rank of A is equal to n, because all the columns are linearly independent and there are n many of them. Now I know that the row rank also happens to be n. Now what is the row space, by the way? The row space is something that sits inside its subspace of, I write this less than or equal to notation to mean it is not just a subset but a subspace of R. I am assuming that the field is R. You can work with any other field, same thing will hold, to the power n, because each row consists of n numbers. Now, what is its dimension? That is n. Dimension of row space of A happens to be n. What can you say from this? Here you have a subspace of Rn and its dimension is exactly equal to n. N is the maximum dimension you can have, that is the dimension of the full space, which naturally forces you to understand that this must be exactly equal to Rn. So whatever vector you give me in Rn, that can be expressed as a linear combination of the rows of A. Very powerful thing, right? It came from the fact that row space and the row rank and the column rank are the same. So this is one example where I moved from column to row. I just switched. So everything can be expressed in Rn as a linear combination of row space. Fine. So I will take this thing E1. So E1 to En, let them be the basis. So E1 to En. Now I like to write my vectors as columns. So since I am going to express it as a linear combination of the rows, I would say E1 transpose, just lying around. That is a linear combination of the rows of A, and I already know how to write linear combination of rows of A. I will just put a vector before it. It's like this, and here are my, no. I will consider A as bunch of rows. So how many is 6? I use 6. So this number multiplies this number multiplies this multiplies this, and so on. So I can write it in this way. Well, the same thing holds about every vector in Rn. So it holds about E2 transpose also. And if I have a list of linear combinations, I have no need to write it again. So I will just put this thing, this is a matrix, is equal to V2 prime. I will go on like this until at the very end. So this says that everything has been taken care of. What is this matrix? Quickly write it down. 1, 0, 0, blah, blah, blah. Suppose n is 4. Then the next one is 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. You quickly recognize it is nothing but the identity matrix. And this is something. I do not care, something. So you get identity must be something VA. Which means if A is a full column rank matrix, there is some matrix such that if you multiply A from the left with it, you are going to get the identity matrix. Such a V is called a left inverse of A. I said a left inverse. This is by no means unique. No one said that all these ways you could take this linear combination as unique. You could take different linear combinations to achieve E1. That's why it's not unique. A left inverse. So full column rank matrices have left inverses. Analogous result, full row rank matrices have right inverses. You can imitate the entire argument, or you might say, well, I do not want to go down into vectors anymore. I have this, I will use that powerful fact of transposing, and I will get the result that full row rank matrices have right inverse. Now, I never like mnemonics in mathematics. I try to remember things conceptually, but this is one thing I can never remember. So I use a little mnemonic. Full column rank L has a left inverse L, and full row rank R has a right inverse R. Very useful result. If you do not have some such mnemonic, when you are doing a bigger computation, you suddenly forget what was the full column rank, has a right inverse or a left inverse. So that's a quick way to remembering it. And if it is both full column rank and full row rank, left inverse and right inverse both exist, then it will be unique, same, and that is what we call inverse, something that we already know about. So let that be the end of the first part of this video. In the next part, we shall take up the rank nullity theorem.